Hey everybody, this is Victoria and Corey. We are the Professor's Du Bois, and welcome back to another video lecture. Today we're going to be talking about the VSEPR model, the valence shell electron repulsion theory, and we're going to get into molecular shapes.
All right, so this VSEPR model, it's really just a theory, and it's based on the idea that electrons, whether or not they're bonded electrons or lone pair electrons, in valence shells, they repel each other, so they try to position themselves as far apart as possible. And that's the premise of this entire theory.
So we have a few electron pair geometries that we want to talk about. Electron pair geometries. So we're talking about where are these pairs around a central atom. So you have to have a central atom, and then where are the things around it to make up this shape. And we have 5 main shapes that we need you to learn. And the first one's linear, and you can see if you have two electron pairs, in this case they're both bonds, they're going to be as far apart as possible. That's linear. If there are 3 electron pairs, 3 bonds in this case, then they are going to be as far apart as possible, and they will be in a plane, and they'll be 120 degrees apart. And we call this trigonal planar. Tetrahedral is the furthest apart 4 bonded pairs can be. In this case, they're also bonds. And this is a little bit harder to picture, and we've got a couple pictures here for you to illustrate here. It's kind of like a how do I even say that? A tetrahedral. There's 4 things as far apart as possible. They're 109 degrees apart.
It's the first time we went into 3 dimensions, because
it is.
The linear and the trigonal planar are just 2-dimensional structures.
Right, so you can see the ones going back into the screen. The 4th one that we need you to learn is called trigonal bipyramidal, and we have 2 3-sided triangles or 3-sided pyramids kind of on top of each other. So we've got the triangle in the center, and then it goes to the pyramid on the top and the bottom. So we have 3 pairs of electrons, in this case bonds, and they look like a trigonal planar in the middle, and then there's one sticking straight up and one going straight down.
Let's call out that, we have some vocab around these positions. So these are called axial position, while the other 3 we call equatorial.
So picture the Earth, right? So we have the axis of the Earth, and picture it straight up and down. So we have the North Pole and the South Pole. Those are the axial positions, and then 3 points around the equator are the equatorial positions. And then octahedral is our final shape that we need you to learn. So we have 6 domains, or 6 electron pairs that are getting as far apart as possible. So we have a square that's in a plane with 4 of them around, kind of like the equator. We don't call them the equatorial positions because they're all the same, but we have 4 in the middle, and then 1 going up and 1 going down, and they're all equidistant. They're all 90 degrees from each other. So we introduced this term domain, and that's a electron pair. So it could be, you can go forward, you can go, it can be in a bond, 2 electrons in a bond, or it can be 2 electrons in a lone pair. So what we do to figure out the shape is count the domains. In this case, we have 4 domains for H2O, and they are as far apart as possible. And if you look at that list, you can see that it's a tetrahedral. It's a tetrahedral electron pair geometry. But the electron pair geometry does not exactly tell us what the molecule looks like. The lone pairs are there, they're occupying space, they're pushing these hydrogens into place, into this tetrahedral position, but if you look at the molecule, if we could look at the molecule, we would just see the H and the O and the H, and that would be a bent geometry. So we have 2 different things. We have electron pair geometry, and then we have molecular shape or molecular geometry. You'll see this as molecular shape, MS, or you might see it as MG, molecular geometry as well.
Or molecular structure.
Right.
And just a little note at the bottom, these lone pairs of electrons do occupy space, and they actually occupy a little bit more space than a bond would. So the angles here would be slightly less than 109.5. However, in our Gen Chem 111, we just go with the 109.5 if we have an electron pair geometry of tetrahedral.
Okay, so lone pairs occupy space. They are domains, and they take up the same positions as the bonded atoms. And the location of those lone pairs normally doesn't matter except for these two situations. If you have a 5-domain structure around a central atom, then the first lone pairs will go in the equatorial positions. So as you can see here, we've got the ones going around the equator. The first lone pair you'd put wherever, as long as it was an equatorial. The next one you'd put also in the equatorial. The next one you'd put in the equatorial. So if you had a trigonal bipyramidal shape and you had 3 lone pairs, your molecular shape would just be linear. It'd come back to linear. And the other one that you have to kind of worry about where the lone pairs go is the octahedral shape. And the first lone pair, it doesn't matter because all these positions are the same. But once you have one of them as a lone pair, the second lone pair will go opposite it. And what you're left with, so if you have an octahedral electron pair shape with 2 lone pairs, the molecular geometry or the molecular shape is square pyramidal, because the top and the bottom, those axial top and bottom positions, are almost like they're not there. You can't see them. They're just lone pairs. And the atoms are occupied in a square.
I think you said square pyramidal, and I think you meant square planar.
I did mean square planar. Yeah, they're all in a plane. There is a square pyramidal with just 1 lone pair.
So I think that what we want to do to start is when we look at a molecule, you're probably going to have to draw the Lewis structure, but we've drawn these for you. First thing we want to do is count these domains. So remember, domains are going to be bonded atoms or lone pairs of electrons. So I have 1, 2, 3, 4. So 4 domains.
First, you go to the electron pair geometry with 4, and that means it's tetrahedral. Then you have to think about, okay, do I have any lone pairs, and does that change then the molecular shape? And it does. So 1 lone pair in a tetrahedral gives us a trigonal pyramidal molecular shape. And the bond angles are from the tetrahedral, 109.5, a little less than 109.5, but we just consider it 109.5.
Okay, here's another one. This is PF5, so I'm going to start out just by counting the domains. So I've got 1, 2, 3, 4, 5 domains.
5 domains is a trigonal bipyramidal electron pair geometry. That's as far apart as those electrons can get. And whenever you have no lone pairs on that central atom, your molecular shape will be the same as your electron pair geometry. So we have 120 degrees around the equatorial atoms, and then 90 degrees from axial to equatorial, and then 180 just between the axials. Hard to see in this position, but it's hard to see 3 dimensions on 2 dimensions, isn't it?
All right, BH3. This is that boron exception when it's got 3 bonds.
Yeah,
but let's count our domains. We've got 1, 2, 3.
Nice.
3 domains.
As far apart as possible, trigonal planar. And when we don't have any lone pairs on the central atom, then the molecular shape is also going to be trigonal planar. So we have 120 degrees around those.
SH6, we're going to count the domains. I've got 1, 2, 3, 4, 5, and 6. 6 domains.
6 domains is an octahedral electron pair geometry. Since we don't have any lone pairs, again, the molecular shape or the molecular geometry is octahedral.
Now I've got an ion, and don't let this throw you. We're going to use the same rules. We can just kind of ignore the fact that it's an ion. I'm going to count the domains around that central atom. So I have 1, 2, 3, 4, 5, and 6. 6 domains.
6 domains, octahedral, but we do have lone pairs, so the molecular shape will be different than our electron pair geometry. In this case, we have the 2 lone pairs that have to be opposite each other, and what we're left with is a square planar shape.
Okay, counting domains. I have 1, 2, 3, 4, 5. 5 domains.
5 domains means a trigonal bipyramidal electron pair geometry shape. We have 2 lone pairs. They have to go on the equatorial positions, and when you take up 2 spaces on the equatorial, you're left with 1 sticking out straight, and the axials going up and down, and that's a T-shape.
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 Okay, we can get into some pretty complicated molecules that have multiple centers. Remember, central atoms are just bonded to more than one thing. So I'm looking at this one. I see 1, 2, 3, 4, 5. I see 6 central atoms. And we just apply the rules for each central atom. So if I'm looking at this nitrogen down here and I counted the domains, I'd say I have 1, 2, 3, 4 domains on that nitrogen. Well, what about this carbon over here? This carbon, if I make that the central, I have 1, 2, 3 domains around that carbon. Same rules apply.
I'd like to point out that the double bond, he didn't count that as 2. We're not counting bonds, we're just counting locations. So that bonded atom, that oxygen, occupies 1 domain. And you don't count bonds, you count bonded atoms and lone pairs. Here's your practice.
I've got some practice for you, and there's something a little confusing here. You'll notice down at the bottom it says, what is the COC bond angle? And when you see something written like this, what they're saying is this is the central. That's the central atom. So I'm just going to leave you with that as a little clue. You're going to have to draw some Lewis structures. That'll be good practice. And let's pause the video. We'll put up the results so you can check your work.
Okay, here's your answers. So these are just the molecular shapes. So you had to go through the steps of write the Lewis structure, count your domains, figure out your electron pair geometry from your number of domains, then look to the number of lone pairs just on the central atom. Ignore the lone pairs on the terminal atoms. They don't matter for the shape around that central atom. Then you can see the molecular shapes that we have here.
All right, and just like most chemistry, a little practice goes a long way. So, if this is very intimidating at first, don't worry, you just need to practice a little bit. There's plenty of practice opportunities out there for you, including some of our materials we have.
And we do have another video on our YouTube channel for just looking at these shapes in 3 dimensions using a simulation. So check that out too.
Yeah, let's put a link to that down below.
It's a good idea. We will. Have a great day. Come back again. Bye-bye.